So how do we tell whether an alternating series converges or diverges? Most of the tests that we've looked at, the comparison and limit comparison tests and the integral test, don't work for alternating series because they require that all of the terms of the series be positive in order to work. However, the test for divergence does work. It works for any series, but it's not often useful. And it will not tell us for sure that a series converges. Fortunately, in the specific case where we have a true alternating series where every term switches back and forth, positive, negative, we do have a test that works for this. It's called the alternating series test. It says if you have an alternating series, the sum as n goes from 1 to infinity of negative 1 to the n times bn, where we assume the bn's are positive. Or, of course, you could swap the signs here and have negative 1 to the n minus 1 times bn. If that series satisfies both of the following conditions, then the series converges. Those conditions are, first of all, that bn plus 1 must always be less than or equal to bn for every n. In other words, the absolute values of the terms must be decreasing, or at least non-increasing. And the second condition is that the limit as n goes to infinity of the bn's must equal 0. Now, we already know that is a requirement for a series to converge, because the test for divergence says if that limit is not 0, then the series certainly diverges. But we also know there are plenty of series for which that limit is equal to 0, but the series still does not converge. What the alternating series test says is that's actually enough. As long as the sizes of the terms are decreasing consistently, and the terms are approaching 0, then the series converges. Now, we need to test both of these things. Either of these two conditions could be true if the other is not. You could have a situation, say a function, where the function is decreasing, but the limit is not 0. Here's an example. Say your function is doing this. And it's actually approaching some asymptote maybe at 1. The limit could be 1, but the function could still be decreasing. So it's important that both these things be true. On the other hand, you could have a function where the limit is equal to 0, but it's not strictly decreasing. Here's an example. And even where the terms are actually all positive. You have a situation kind of like perhaps a sort of a decaying sine wave that is always getting closer and closer to the x-axis, but is always going to go back up a little bit. It's just the humps are smaller and smaller and smaller as we go. So you need to check both conditions. One could be true without the other. Let's apply the alternating series test to our alternating series. So we've looked at this example before. The sum as n goes from 1 to infinity of negative 1 to the n minus 1 times the natural log of n over n. Now, this is interesting here because we can't really tell from looking at it whether the limit of the terms is going to 0. But also, more importantly, the absolute value of the terms is not actually decreasing in the beginning, right? Ignoring the signs here, we have 0.347 is actually greater than 0. So that means that our B2 is greater than B1. In fact, 0.366 is greater than 0.347. So that means that our B3 is greater than B2. After that, however, it looks like, from the terms we've written out, it looks like our B4 ends up being less than B3, B5 is less than B4, and so on. It does appear that the terms start to decrease after B3. But again, we're not quite certain of that. Now, with all of these tests and all these series, if the tests fail for the first, say, 10 or 100 terms, that's okay, as long as after a certain point, looking at all the terms after that point, as long as the conditions of the test are satisfied after a certain point, then you're good. Because what we're looking at here is the end behavior of the series. What happens in the first few terms doesn't actually affect whether the series converges. It does affect the sum, of course, but not whether the series converges. So the fact that we have a few terms in the beginning here that do not decrease is not a problem as long as the rest of the terms decrease. But how can we tell? Let's try and figure this out. This is an alternating series. And our BNs here are basically just every part of the series that doesn't involve the negative 1 to a power, the sign. It's actually the absolute value of the terms here, and that's going to be the natural log of n over n. So the first question is Bn plus 1 less than or equal to Bn for all n? Well, actually, no. The answer is no, because B3, we determined, is greater than B2, which is greater than B1. So what about if we look at just for all n greater than 3? This, it turns out, will be sufficient to make this work. As long as all n values greater than a certain point work, we're fine. So the question is this function decreasing when n is greater than 3? Well, we can figure that out by using some calculus. Let's let f of x equal the natural log of x over x. How do we know whether a function is increasing or decreasing? Simple. We take the derivative and find out if the derivative is positive or negative. So f prime of x, the derivative of this function, we'll just use the quotient rule. That's going to give us 1 over x times x minus the natural log of x times 1 all over x squared. And that simplifies to 1 minus the natural log of x over x squared. Is this positive or negative? And when is the natural log of x greater than 1? Well, the natural log of x is greater than 1 if x is greater than e. The natural log of e is 1. Any x is greater than e, the natural log will be more than 1. So that means that 1 minus the natural log of x is negative if x is greater than e. And x squared is always positive, so that means that f prime is negative. It's less than 0 if x is greater than e, which is, of course, approximately 2.718. That tells us that our function is decreasing as long as x is greater than e. So the answer to this question, is the function decreasing when n is greater than 3, is yes. Three is greater than e, so if n is greater than 3, it's certainly bigger than e. And our function is decreasing then. So we've just checked that as long as our n is high enough, yes, bn plus 1 will be less than or equal to bn, as long as n's high enough. That satisfies the first condition. Next condition, what is the limit as n goes to infinity of our bn's, of the natural log of n over n? Well, if I try and plug infinity in now, I'm going to get infinity on the top over infinity. The natural log of infinity goes to infinity, of course, and is infinity. So this tells us, this is not an answer, but it tells us that we can use L'Hopital's rule. So this is equal to the limit as n goes to infinity of the derivative of the top over the derivative of the bottom. So that's going to be 1 over n over 1. Now as n goes to infinity, we're going to have 1 over infinity that goes to 0. So the limit as n goes to infinity of our individual terms is 0. And since both conditions 1 and 2 are satisfied, the alternating series test tells us that our series converges. Now let's look at our second example. The sum as n goes from 1 to infinity of n cosine of pi n. Now we determine that this series is just negative 1 plus 2 minus 3 plus 4 minus 5 plus 6 and so on. It is an alternating series, but it actually fails both conditions of the alternating series test pretty obviously. In particular, if we check condition 2, the limit as n goes to infinity of our bn's. Well, our bn's here are just n, right? It's just 1, 2, 3, and so on. You're stripping out the negative signs from these. That is the limit as n goes to infinity of n, and that is infinity, which is not 0. In fact, by the test for divergence, this series diverges. How about this last series? The sum as n goes from 1 to infinity of cosine of n over n. Well, the problem is, as we determined before, this is not an alternating series. None of the tests that we've learned so far, nor any of the tests that we're going to study later, will actually work for this series. So it is hard to tell whether it converges or diverges.